Great. Okay. So we can start, I guess. And just I am Ashfaq Farooqi. I am currently a PhD student at Chalmers University. My research focuses mainly on autonomous systems. Uh, yeah, I guess before we begin, it's good to say that you if there's something you don't understand during the presentation, just post a question on the group, on the chat, and I guess someone can, maybe Anil sir can just handle everything of unmuting and speaking up so that we don't create chaos. Uh, and he can be the moderator, I guess. Is that possible, Anil sir? Am I audible? Can someone just unmute and tell me?
Yes, it is audible.
Okay, good. Uh, yeah, so I guess Anil sir can just coordinate the session and post questions if there is any. I will take questions mainly at the end, but if there's something unclear during the presentation, I guess it's, just raise it then and there and we can solve it. Uh, so yeah, I would prefer it being more of a constant conversation, but given the current medium we have, it might become tricky to have a full-fledged conversation. Uh, but we try to do the best with what we have. Uh, so yeah, so I passed out in of BMSIT in I think 2012, and then I did my master's at Chalmers in mechatronics, and I continued there as a PhD student. My area of research is mainly supervisory control theory, and within that, learning of models. Uh, I will not talk exactly about my research here, but I will show you the problem that arises, which I try to solve. The talk itself is going to be quite broad and general. And yeah, as I was told, I aim to present this for mainly final year and pre-final year engineering students, mainly from EC branch, but the work done here is contains a lot of computer science. So there is a mix, and I think that's one element to highlight here of how different areas start overlapping with each other. Mainly when you get into autonomous systems and these kind of areas which are a big overlap of many different things. Uh, so yeah, I will if there's any questions later on, you can always contact me on my mail address, and we take it from there. We start, I guess. So the main direction or outline of this talk is going to be, as I said, really broad and something where you can take away and try to do something in the real world with your own projects, maybe even as a final year project. You can think of using the tools and ideas I speak about here. So we start with so during the talk I will introduce to you why we need reliable systems and what are actually reliable systems, uh, and then I broadly show you different tools and different techniques that are used to build for building reliable systems, specifically proofs, verification, and synthesis. Uh, then we go take a small dive into supervisory control, which is one of these elements, mainly with synthesis, but also has overlaps with verification. Uh, we come to the definitions of each of those. Uh, and since I wanted it to be a little more hands-on, I will try to give you a step-by-step procedure to think about building reliable systems using the framework or tools which I talk about. Uh, I will show you one example of how this supervisory control has been used in the real world, mainly with autonomous cars. And this is a project we had in my research group. Yeah, and then we go look at the problems this method faces, and before we conclude. So, just to introduce, we've made a lot of mistakes in our past as engineers. Uh, I'm sure many of you know the Boeing 7, I think it was, sorry, that's a typo there. It's the Boeing 747, which recently crashed after liftoff. And these were two consecutive crashes in the last few months. Uh, the problem was that they had two sensors for a particular system, and they thought it was redundant to have two sensors, and they pulled out one sensor. Uh, but they never went in to check what actually impacts or what impact this one sensor had uh, on the system, uh, which led to the two fatal crashes. And also, it was yeah, so there are a number of problems that arise, right? Who is to blame? What happens? Why? But at the core of it, the software they had was not well tested. And I will highlight some bits about testing, but we don't talk so much about testing. Uh, More so, what can we do to solve these problems? Uh, and how do we ensure that removing one sensor was not or should not have been the fault? Uh, Another bug was the Mars orbiter. I think this was in the 90s, late 90s. Uh, so this was a joint collaboration between several different companies, and it was mainly headed by Europe, the European Space Agency. But they had one element that was to be developed by Lockheed Martin in the US. So what happened was in the US they use, I think, the SI system or the metric system, and in Europe it's the other way around. And so the people in the US built it for their own metric system and got the module, and the Europeans plugged it in and they sent the Mars orbiter into space. And once it was out, there was a crash because the values were totally different and the computation went bonkers. Uh, Again, a simple error. No one actually thought about this, or yeah, even if they did, it wasn't brought to the attention. It went unnoticed, and it costed a fortune. And it was just a small blunder as to what metric system should we use, and it wasn't consistent throughout. Uh, the Pentium 2, I think, came out in 94 or 93, but a bug was found, and apparently it was called the floating point division bug. And this was actually a hardware bug that was implemented in the Intel systems, and it costed Intel almost 45 million, and they lost their reputation during that phase. So during that time, Intel actually built up their whole formal methods division, and formal methods is what I will be talking about later, uh, to actually encounter bugs like these. And so yeah, again, a very big flaw or a bug which caused huge damages to industries and yeah, other areas. Uh, the Ariane 5, which was a space mission again, and this crashed 45 seconds after launch. Uh, the problem here was the navigational unit that was in place had some old legacy code. The engineers thought that going from Ariane 4 to Ariane 5, they want to retain most of the software, if not all. So this navigational system was retained, but they never thought about the consequences of having the software there. Everyone assumed that it was needed for the system to work. But once it was, yeah, a few seconds after launch, it went into It exited the Earth's orbit, I guess, and exploded. It was quite drastic. The visuals are scary. Uh, anyway, these and yeah, there is. I want to bring up pacemakers, which I mean, the other bugs you saw seem far removed, right? But pacemakers and other medical devices have become part and parcel of our life. Uh, so, pacemaker is a device that basically simulates heart beat, gives electric pulses to the heart when it thinks the heart isn't pumping, just to stimulate it. So, what happened was most of these devices are built for unfortunately, are just built for men and built by men. So they don't take into consideration other factors and different specifications. So there was one woman who she was pregnant during that time, and apparently during the pregnancy, the heart rate has or the heart has certain kind of fluctuations which the pacemaker thought that the heart was actually stopping. So it gave extra stimulus, and it wasn't fatal for her, luckily. But things like these as to what determines a system to be reliable. We have a lot of technology around us in our life, uh, and which we depend on heavily. So, are these systems reliable then? How, to what extent can we rely on them? And when I say reliable, I mean trust them completely to behave exactly as they should. Uh, and yeah, uh, so that was the problem with pacemakers. They did not take into consideration certain specifications of people or a certain group of people, and that's where we need more diversity also. But that's a different topic altogether. Uh, so reliable, we need systems which are more reliable. Uh, and yeah, we've seen a lot of errors, a lot of bugs throughout the area ages, and I think these are the most famous bugs. Uh, just do a Google search and you will see bugs that have costed a lot of life and yeah, money to companies, stock market crashes, and whatnot. Uh, so the idea behind it is, can we ensure these mistakes don't happen again? Uh, we know humans are not possible to, or humans cannot fathom all the possibilities that can go wrong. Can we then use computers to do this for us? Can we make computers give us a certain amount of confidence on whether a system is reliable or not? Uh, so that's why we need reliability in our systems. So what we or where we go from here is to have mathematically defined systems, systems which we can use, systems which have certain mathematical properties that tell it that tell us that the system is reliable. Can we find these properties, and can we build systems that embody all these properties so that they are reliable? So this is the next phase, or the ongoing phase in the industry right now. Most of the industries have started switching to model-based design. So what is a model? In my talk, a model is basically going to be the description of the system and its behavior. What a system does, maybe how it does it, and it can be at several different levels. From a high level, it can just be doing different tasks. You can go to a much lower level and see exactly what the control system is performing at a given time. But all this can be formulated in a mathematical formula, or mathematical theory in itself. Uh, so once you have the behavior of the system as a model, you also need the requirements the system should uh, adapt to, or should behave according to. And these are called the specifications. Again, these are mathematical in nature, and they, together with the model, uh, can be used to ascertain how well the model fits these specifications. So now we've basically transformed our problem from a physical domain where you have a controller, and a controller is any system which takes in sensor inputs and produces actuator outputs to control it. Uh, every pacemaker has a controller, the airplane has several controllers. Uh, every system, every cyber physical system has a controller. And when you design a controller, there is a set of requirements that come along with it. So the main problem or the question is, does the controller satisfy requirements? Which is very broad. And for us humans, it's hard to determine if it is always right. But we can transform this question by transforming the controller to define a model, where the model defines the behavior of this controller, and the requirements become the specifications. Uh, and then we can ask the question, does the model satisfy the specifications? And the second question is completely mathematical. So we can use tools and techniques we have been developing over the years to answer these questions. And this will be done by computers, and we have a certain degree of reliability on these systems. And that's the gist of how we go towards building reliable systems. How do we give guarantees on whether a system is reliable or not? So if we go to the next stage, uh, deductive proofs. I will not cover too much on this topic on proofs, but I just wanted to show it to you to give you a flavor of what is out there. The what you are given with is a program. So if you see here, we have a small piece of program in between these lines, which is a simple if condition. So if b x is 1, else x is 2, and then at the end y is 3. Really simple, just to show you how things work. And you've defined x and y to be integers and b to be Boolean. So you want to check if after the execution of this program, whether y is always greater than x. So this here becomes your specification. So you have a specification and you have the program itself. Just to be clear here, this is not a model, but this is the actual program you write for your controllers. So yeah, the question then becomes if you can prove that this is always the case. And the proof would, you have proving techniques, and it usually looks like this. It's a bit complex to understand, but I just wanted to show you that there is a way to prove that this program behaves as it does. Though this is a very simple case, think about really complex if-else conditions, and there are complicated scenarios. One example would be the sorting algorithm in Java. So the Java standard library has a sorting algorithm pre-built in it. And there were researchers from Netherlands who proved that there were certain bugs in these sorting algorithms. And the proof was derived from this tool, which is Key here. It's called the Key project if anyone is interested in. But where does this take us, and why am I mentioning this? The future seems to be in blockchain, at least when it comes to enforcing contracts. And this system has been called the contract-based system. So you define a contract, and a contract is basically a specification saying, my program, when given an input of certain type, will always produce an output of a particular type which satisfies certain requirements. And given this contract, it is legally enforceable. So the platform Ethereum, which is currently online, they work with these contract-based systems. And I think there's some noise. Can you please mute your mics? Yeah. So yeah, Ethereum is one such platform which has been developed for contracts, and these contracts are legally enforceable. So they work for stock markets, for example, transactions between people, and all this uses blockchain. So if you make a mistake, it lives there. So you want to be 100% sure that these contracts are proved to be correct. There is no uh, error in the program itself, because if there is an error, it will just continue through the blockchain and propagate itself. Yeah, so this is quite different from what I'm going to talk about, but it's just so that you get uh, a feeling into what exists out there. Uh, but yeah, let's come to verification. So verification talks about uh, answering questions of the type where, given a specification, is this specification always valid or not? And if it is not valid, then the system, the verifier in this case, will give you a counterexample to show that the system does not behave as it does. Take this example here. We have a simple uh, vending machine example. So you have at the start the system is idle, and when you insert a coin, you get to select whether you want, say, cola or water. And depending on what you choose, you get the item, and the system goes back to idle. One example of such a specification is you get a drink only after providing a coin, and this is satisfied in this case, right? Because you always need a coin before you get anything. Say the programmer had made an error in moving this get to a select, or say making the initial state the select state, then you would get a counterexample. And that's the idea of verification, uh, to at every stage get a confirmation whether your specification is satisfied by your system or not. Uh, and this is a slow step-by-step approach where you start. And once you, for example, once you get this counterexample, you will take it into consideration and redo your model, and then check it again. And you will continue doing this till no other counterexamples are formed. And when there are no counterexamples, you know your system is reliable for the given specifications. So this is one approach to developing or for verification. We have another one called synthesis. And synthesis basically comes from supervisory control. We get into that a little in the next slide, I guess. Uh, Take, for example, the stick picking game. What the stick picking game says is you and your friend, two players, want to play a game, and in this case, with say 5 sticks, the person who picks up the last stick is the winner. So you have a model that basically says you are player one and you start. So when you take a stick, you can take either 1 or 2 sticks, and those are defined by the transitions here, right? And then the player two can take 1 or 2 sticks, right? And then you want to check, or what you want to do is you want to find an optimal strategy, or it need not be optimal. You just want to find a strategy where player one wins, that is, you win. And this is your strategy. So since you are player one, you have control on what you do. You can either pick, remove 2 sticks, or you can remove 1 stick. What you get out as a synthesis example is you should always start with picking 2 sticks, and then you don't care what your opponent picks. He can pick either one or he can pick two. And whichever one he picks, there is a guaranteed strategy that you will win the game. Uh, and here, what we have already defined is that what you can do For example, here player one remove two and player one remove one. These are called controllable events. It's something you have control over. Events of the player two, so that is player two remove one and player two remove two, are uncontrollable according to you because you have no say in what happens. So you have to allow all possibilities of uncontrollable events here. So if you take this supervisor, and the supervisor is also, in a sense, the controller, to run it on your system, to be the person, to be the element that controls you, then there is always a guarantee that you will reach what you desire, which is the specification where you want it to win. And hence it is a reliable system, right? If there is no possibility, the system tells you that it is impossible to have this specification satisfied. So unlike verification, where verification gives you at each stage a counterexample disproving your specification, synthesis removes all counterexamples at once and gives you a final result. These are two different approaches, and both have their own, uh, yeah, pros and cons, and you need to choose which one works best for your system which you want to develop. So that was a brief overview on the different proving techniques, or yeah. So it's basically called model-based systems, right? Formal methods, and those are largely the most common systems. You have several others, but we don't get into those right now. I think these give you sufficient stimulus to start uh, trying out one or the other. So, supervisory control. Uh, I tried not to have any equations, but I could not avoid this one here. It's a definition, so please bear with me. I will try, yeah, giving everything with examples, and yeah, this should be the only equation you see in the control in the whole presentation. Uh, so supervisory control was developed by Peter Ramage and Walter Wanham in the late 80s. What and where this the idea comes from is was actually it can be traced back to, I think, the 1950s, where there was a DARPA project, and there that was where the first AI as a term was coined for the first time in the 1950s. And this project actually brought together a lot of people working on different areas, neural nets, some amount of machine learning, automata theory, which and automata theory is what we are interested in here. Automata theory was back then used to define languages, mainly natural language. So the famous researcher Noam Chomsky, he formulated the use of automatas to describe languages, and yeah, so that's a whole different field. But what is interesting is Peter Ramage and Walter Wanham actually found a way to use these natural language definition systems to apply it to controlling of systems. And this is basically for discrete event systems. So automatas can represent discrete event systems in a very complete or thorough way. Again, discrete event systems, if you did not follow, was any system where we can discretely define the steps, like in your stick picking game we saw previously. So each action done by you was a discrete event for the system. So you have a lot of systems that behave as discrete events. You have your vending machines, your microwaves. Yeah, a whole lot of systems are can be classified as discrete event systems, and they can be controlled in using supervisory control theory, among many other control strategies. So just coming to the automaton. What is an automaton? It is a collection, a tuple of set of states, and states here represent the circles what you see here. These two are basically states. The elements here, the actions what you see here, they're called events, and all the events in the system are composed of the alphabet. This alphabet has something which is the controllable event set, which is what you can control. For example, in your case, your own actions in the stick picking game, and the uncontrollable set, what you cannot control, the actions of player two. A transition function, which basically says how you go from one state to another. So this is a transition, right? So you go from state player one to state player two by performing player one remove one. So this is a transition. So you have a set of these transition relations, and you also need to know the initial state. Once you have an automaton, and as I said, the automaton was used for languages, you can define the language of the system. So the language of the system becomes all the valid combinations of the alphabet in the automaton. It's not very important to get into that. Let's, yeah, if there's any question there, we will take it later. Let's take another example here. So we have two machines, three systems, and the machines are set up in such a way that a product enters from the first machine, M1, and machine M1 does some amount of processing over it. For example, it could be a robot that is gluing two elements. So the product enters into machine one, the robot applies the glue, and then the machine one sends it out. It unloads the system into a buffer. So a buffer has a certain capacity, right? It can have a certain number of processed parts in it, and that is held there. We come to the buffer in some time, and from the buffer, a second machine can take it, and let's say the second machine is doing the pressing operation. So once you've glued the two parts, you want to press them together, just as an example, and then it can unload the part out. All of this can be shown in these three automatas you see here. So M1 defines the machine, and 0 defines the initial state, and 1 is the next state. So when a product enters, it can be loaded first into the machine. Some processing happens here, we don't care. And then it can be unloaded. So the unload here is, it's an uncontrollable event. You don't know when the machine is going to complete its task, and then it unloads the system. So anything you see with an exclamation here is an uncontrollable event. The same can be said for machine 2. It behaves in the exact same way, right? It loads a system and then unloads it out. The buffer here has a certain capacity, and in this case, we have capacity 1. Some object moves into the buffer only when the machine 1 has completed. That is, unload has been performed. So when unload happens, the buffer becomes full. And when load 2 happens, the machine 2 is loaded, the buffer is again gone to empty. You will see the complete graph for this in the next 2 slides. But so overall, this is how your system works, and this is how you will model your system. Language, if anyone is interested, for M1 is all the possible combinations of this load 1 and unload 1, which are accepted by the system, which is load 1 is part of the language, load 1, unload 1. So you do load 1 and then unload 1. And then it continues, right? So you have load 1, unload 1, load 1 again. And then it, yeah. So that it's almost sort of an infinite language. But that's besides the point. So you have your system, and supervisory control theory has certain properties it can give to the system. And the two properties here are controllability and non-blocking. So according to controllability, only some parts of the system can be controlled. As we previously saw, it was the load 1 and load 2 can be controlled. The unload operations cannot be controlled. So we already know what can be controlled and what cannot. So you want to ensure your final supervisor is always controllable. And by saying always controllable, I mean, as you saw in your stick picking game, you allow for all uncontrolled possibilities in your system, and then ensure that you are the one directing it to go or meet the outcome you require, which is defined by the specification. Uh, Again, I did not want to get into the mathematics of this, which is very important, but yeah, writing it out in natural language has the effect of making it not so right. But just to give you a gist, if you're actually interested in the actual equation which defines the controllability, yeah, let me know. I can direct you to where you can find it. Non-blocking is a very essential property in many systems. You want to ensure that your system is never stopped. It shouldn't deadlock at any point. There should be no sequence after which it finds nothing to do, right? Either the final state should be your marked or target state, like in your stick picking game, you should be the winner. That will sort of be a blocking state, but since it defines it is what you want, you yeah you need not consider it as a blocking system. But in your machine buffer and machine, you want to ensure that the system is always uh, ongoing. So every time a new part comes, something has to keep happening. It shouldn't stop for any reason, and yeah, without any possibility to go forward. So supervisory control guarantees these two properties under certain conditions. And yeah, those conditions are a little bit mathematical, but suffice to say that if you have a system, uh, you can get a controllable and non-blocking supervisor for it. And yeah, we see what I mean by that. So what you see up here, the synchronization part has the complete behavior of your machine buffer machine. So it starts here in your initial state where the buffer is empty and both the machines are idle. You load a part, so load 1 happens, and the buffer is still empty, but machine 1 has started working and machine 2 is still idle. At this point, all you can do is unload 1. There is nothing else you can do. So let's say unload 1 happens. This is an uncontrollable event. When unload 1 happens, your buffer is full and the two machines go back to idle. At this point, you can either have a load 1 happening again to fill up the first machine, or you can have load 2 happening. This refers to this point here. So you can have load 2 happening. And when load 2 happens, you have the buffer is still empty, or the buffer becomes empty, and the first machine is idle, the second machine is working. And if the machine 2 also unloads the part, you go back to your initial state. But since the buffer can have one additional part, you can always load another system. So now you have both machine 1 and machine 2 working and the buffer empty. Let's say you unload from machine 1, which makes your buffer full, and yeah, machine 2 is still working. You can again load your machine 1. So you have a full buffer, and you have both machine 1 and machine 2 working. But the problem here is unload 1 is a uncontrollable event. So machine 1, since it is working, it can throw out a part. And if a part is sent out, the buffer cannot accept it because the buffer is full. So this becomes a problematic state. We do not want to be in this state. And the same holds for this. Here, machine 1 is working. You don't know when it will be complete. The buffer is full. So if unload 1 happens here, there is going to be a crash in your buffer. So you want to avoid these two states. That's why it's marked in red. What you can do is you can synthesize a supervisor, and this is what SCT, Supervisory Control Theory, talks about. You generate a supervisor which ensures that there is no possibility of getting into these bad states. So if you take out these two states and all uncontrollable events reaching here, you end up with this system. And if you control your system using the defined supervisor, it guarantees you that you will not come across problems like these. So there is certain amount of reliability already put into the supervisor. So that's supervisory control in broad. Uh, so now just to give you a highlight of when you go ahead to develop your own systems, how should you think and what approach should you follow? Uh, I've spoken about three techniques broadly. There are several more you can read up upon. But pick one or more that is relevant for your application. See what you need and choose the tools that make sense for you. Uh, First, start off with developing a model for the behavior of the system. So what should the system do? How should it behave? What are the inputs? What are the outputs? Start chalking them down. Uh, very For us as engineers, it's very common that we start off by programming the first thing what we do, but that's usually uh, not a good strategy. You start with modeling, and these are basically what we try to do in the industry as well. Uh, Once you have the model, you translate it into, and you then translate the requirements of the project into specifications. So now you have a model, the behavior of your system. You have your specification, that is the requirements posed by your third party, your client, or yeah, whatever the project you have in mind. Uh, you need to verify and update the model till the specifications are satisfied if you're going for the model checking technique. On the other hand, if you're going for the supervisory technique, you need to ensure that the supervisor captures the behavior you want. And this is the tricky part here. Uh, yeah, of course, this requires tuning of point 2 and 3 continuously till you get something you think works fine. And only after that, what we from the academic community want to do is be able to generate programs automatically from here. So once you have the model and you have the specifications and you go through this whole process, there should be a way to automatically generate program code or controller code that can be run directly. Uh, MATLAB has some functions for this, but it's all research here is mainly very what do you say, application oriented. So given an application, you have a use case or you have a auto generator, but that's not always possible. Uh, so this is a huge area of research to automatically generate code from models and specifications. Uh, yeah, so yeah, we have time. So one example I want to give from the real world is the lane change algorithm in autonomous driving. So there is a project in my group, and they are working on self-driving cars, basically. And self-driving cars can be viewed as a cyber physical system, right? You have some sensors, and then some amount of fusion is happening to determine the position of the sensors. Say, for example, this is where all the deep learning and machine learning and yeah, all of that happens. The output of this is given to a high level controller, and the high level controller decides what needs to be done next. And it also keeps track of where it is in the system. What is the car doing? How is it behaving? What strategies it should use next to continue driving safely. Uh, Based on the decision of these controllers, high level controllers, signals are sent to the actuators that actually perform the actions. Uh, in this case, we have a lane change system, and lane change is basically when you have to overtake another car, right? Uh, so there are certain rules it needs to follow, and which basically mimics how we humans overtake. Uh, so you have to indicate to whichever direction you're moving into, and then move into that required direction. So we are dealing with this one example of lane change system, and we want to check whether the lane change algorithm they have is behaves according to specifications or not. So yeah, this was just a overview on this. This was a student project, and what they did was they took program code from the actual implementation of the controller, and they derived a model for it. They derived a mathematical model that defines the behavior of a program. Uh, the program was, or the model which came out had 1.4 into 10 to the power 5 number of states. That's pretty huge for the total number of states. And yeah, so once you have this system, they defined a specification, and the specification basically says that every time you do this update, the direction you are changing into should be equal to the request you have. So if I am moving left, I should always have left as a requested direction. In case the direction is not same as the request, then we have a problem here. So they put the specification, plugged it in, and let the computers do their work. Uh, you ended up with almost 3 million states. Uh, 1 million of them were unreachable. But what was interesting was they found a scenario in which the car would indicate left, but then turn right. And this was not, of course, this was not intended, right? It's something the car should never do. And it gave you the program gave you a counterexample as to why this happens. What is the exact sequence of events that happen leading you to this error? And it was counterintuitive. It is impossible for humans to actually think of all these 3 million states and come up with the perfect solution. So now we found the error, and then they try to fix it and yeah, resolve it. So once you have this system, you can actually say that you have a reliable system according to certain specifications. In this case, this particular specification. So this is one example that has happened, or that is currently an ongoing project where we are yeah, trying to solve these systems. Uh, just before we wind up, yes, we still have a few minutes. Uh, what usually happens, or the problem, is that there is a state space explosion. For really small systems, you end up with a huge number of states, and sometimes the states cannot be computed. And this is an NP hard problem. It's proved to be NP hard, and nothing can be done about it. So if there is a small system, we can verify it, but as the system grows, it becomes harder and harder to solve the problem. Uh, we are working on techniques to resolve this, to try to do it in smaller batches. Uh, but yeah, there is a big research gap here, and yeah, there's always room for improvement, right? The other problem is how to create these models and who creates these models. It's not easy to come up with a model defining the behavior, uh, and who should do it. What skills are needed to define these models? Uh, and, and a whole bunch of questions open up when you start trying to think about a model, because models are going to be an abstraction of your reality. And in this case, the what do you say? Um, yeah, uh, it becomes hard depending on the system where you want to abstract it out. Uh, and the third problem is specifications. It's almost it's really hard for humans to think about all specifications and come up with them. For example, in the pacemaker problem I discussed first, unless a doctor knew the specific problem of pregnant women, they could not come up with a specification to satisfy it. So there is need to there is a research need for developing specifications. And of course, specifications come up as natural language, right? Player one should win. That is a specification. But to translate it into a formal specification is not always the easiest task. So, out of these, my research focuses on creation of models, just to yeah, give you a hint. Uh, so I'm looking at automatic ways of developing models from a simulation of the system. Uh, so that's yeah, that's where I stand. Uh, just to conclude, so we spoke about how automata are a way of modeling discrete event systems. They are one of many ways, but they have a lot of good properties that can be leveraged to guarantee the reliability of systems. Uh, we have tools like model checking and supervisory control to use the automata and generate a controller uh, satisfying several or many requirements. Of course, the problem is state space explosion, and this is yeah, it it can just be eased, never solved. Uh, but also lack of models and yeah, obtaining them is a challenge, right? Uh, yeah, I guess I will stop there for questions if there are any.
Hello, Ashfaq.
Yes.
Yeah, you were talking about pacemaker, right?
Yeah.
Why, when they release to the market, they are supposed to test in all the conditions.
Yes. So that is the difference between testing and formal verification. So
Okay.
testing can happen with a given set of inputs. For
Hmm.
example, if you want to test whether a plus b is always equal to c in a program you have written, uh,
Okay.
you can test only from 1 to 10 or 1 to 100. But
Hmm.
what formal verification does is you will prove it for all integers.
Hmm. Okay. Shubham has some question.
Yeah.
How can students start off in such a field like supervisory, reliable systems, automotive? Okay.
Yeah, so I mean, this is a very niche topic. It's been mainly in academia. For starting off, I mean, yeah, there are several courses that, what do you say, discuss these problems. and yeah, there are some courses on Coursera and EDX, but it's hard to find resources on them.
Mm-hmm.
Uh, and yeah, it's just one of many ways in developing robotic systems, right? So most of the robotic courses actually uh,
Okay.
delve into these problems. So they give an introduction into this.
Yeah,
Uh,
what kind of problems can you suggest to our students to take up projects in final year? Like 1 year time, in 1 year you can complete some autonomous vehicle, some problems related to autonomous.
I mean, of course, there are a lot of
Just now I noticed that one lane problem, right? Lane
yeah,
crossing indicator, okay, those kind of things. Uh, like that, if anything, they can make it for final year project and something. It's like novel kind of designs or novel kind of algorithm.
yeah. I mean, there are a lot of opportunities, but it's hard to pinpoint.
Mhm.
Mainly because I mean it requires some amount of delving in, right? So, for example, there you could think of ways to model systems. That is in itself a big research project. Uh, Given a system, given any kind of system, actually, how do you model it? And once you model it, can you show that it behaves in the right what do you say, a reliable way? Uh, so these are the kind of problems we deal with. And so for students as such, if you're talking in terms of supervisory control, you have a lot of algorithms that deal with them. Uh, so you can think about developing or improving on the existing algorithms. Uh, and if you're thinking about autonomous systems, there I would just say it is left to one's imagination. So I guess any idea on autonomous system is interesting to given the current time, right? Self-driving cars, as an example, is a perfect scenario.
Like what I heard is the program modeling or state machine models or state machine diagrams. There are tools available. Just if I give specification, it will give some options, right?
Yes, yes, yes.
Okay.
So there's one tool called NUSMV
Mm.
uh, that is for model checking. Then there is Supremica for supervisory control.
Mhm.
So yeah, tools exist, but they've been confined to what do you say, academic research for a very long time. Uh, so if you have a problem in mind, you can always use these tools to uh, yeah, check whether your system behaves according
Any
to the
open
spec.
sources available for students?
Most of these are open source. So NUSMV is open source, Supremica is open source, TCT is open source.
Um,
Yeah, so most of these, what do you say, programs within academia are open source. And I guess the communities are really helpful. If you just send the mail to the person developing the tool, they are usually happy to help.
okay. Any international journals which are standard like for this autonomous or control theory kind of which journal you prefer?
So you have TACE, transactions on autonomous, uh, I think it is autonomous systems engineering. It's an
Days.
IEEE. It's called TACE.
Any questions, audience? You can unmute and
Okay. So just one thing. Uh, just give me a